Now, what's the effect of this on SN1 and on SN2? Let's see here. Let's say that we have a nucleophile. Now, the nucleophile is going to be solvated. That means it's going to be surrounded by solvent molecules. But it might be loosely solvated, or it might be tightly solvated. So here is a loosely solvated nucleophile. There's solvent molecules around, but there's still some gaps. And here's a tightly solvated nucleophile. This is what we would call a solvation shell. There's almost no gaps around it. Now, who is more likely to form this solvation shell, the protic or the aprotic solvent? Who's likely to be a better solvent? Someone who can form hydrogen bonds or someone who can't form hydrogen bonds? Who's going to form this tight shell? Sorry?
One with a hydrogen bond?
Yeah, remember, what are hydrogen bonds? They're strong intermolecular attractions. Well, if you can form strong intermolecular attractions, you're going to form as many as you can, forming a tight shell around the nucleophile. So this would tend to happen with the protic solvent. The hydrogen bonds are what allow it to form such a tight solvation shell around the nucleophile. Whereas an aprotic solvent, it will only loosely solvate the nucleophile because it can't form as strong intermolecular bonds. It can only form weaker bonds. It can't form those strong hydrogen bonds. So this will only be weakly bonded, and therefore there'll be more gaps and more space around the nucleophile over here. Okay, so here's our polar protic and aprotic. Now, what was our big obstacle to SN2?
Steric hindrance that blocks the nucleophile.
Steric hindrance that blocks the nucleophile. So which of these is going to form an obstacle to SN2?
The protic solvent.
Here's all this steric hindrance that blocks the nucleophile. So what type of solvent is best for SN2? Okay, so that's the upshot right there. In organic chemistry, you have to know the patterns, but it's also important to understand them. Partly because you might be expected to explain them, but also just because it makes it easier to work with them. So aprotic is better for SN2.
Question?
Yeah.
So if we put ethanol, it'll still go through.
In this case, yeah. In most of the cases that you would be given as a test question, SN2 would still work with the protic. It would just be slower.
Okay. So the rate is the only difference between them?
Yeah, it would be slower. Now, in the real lab, there might be situations where with an aprotic solvent, you can just barely get the SN2 to go. And then if you shifted to a protic solvent, the SN2 wouldn't work at all. However, you're not too likely, as just a practical class matter, you're not too likely to see those examples given to you on test questions. So the point is, usually on test questions, the solvent is not a decisive factor. It just speeds things up or slows things down. In a real practical situation in the lab, it could be decisive, but instructors just don't tend to write questions like that because you couldn't be expected to know when it would be decisive and when it wouldn't be, basically. So even though in the lab sometimes the solvent would be decisive, you're not going to be tested on that, most likely, unless the instructors really emphasize that in class. So usually all that they would expect you to know about the solvent is whether it's going to speed things up and slow it down. But they're not going to expect you to know when it would be decisive. So we'll usually assume it's not decisive. Again, that's why in the table in the handout I didn't even include the solvent, because usually that's not the decisive factor on test questions, which is kind of what we're preparing for. Okay. All right, so this would be better for SN2 over here. All right, so looking at this over here, we already predicted this would be an SN2. Fast or slow? Based on the solvent. Yeah, we expect this ethanol is going to slow us down somewhat. We expect the ethanol is going to slow us down because this is not the best solvent we could have. This is a protic solvent over here. It would be better to have used an aprotic solvent. So we're still going to predict SN2, but we would predict it would be faster if we used an aprotic solvent. And how about in this case, would we predict fast or slow based on the solvent? Fast. We would probably still predict SN2 even with ethanol, but it would be slower. Okay. This is probably going to be pretty fast anyway because there's so little steric hindrance from the substrate over here. Okay. Well, while we're at it, let's think about what was the big obstacle to SN1?
Is the stability of the carbon cation.
That's right. The big obstacle to SN2 is steric hindrance that blocks the nucleophile, but we also discussed last time the big obstacle to SN1 is stabilizing the carbocation. Remember, the nucleophile doesn't make much difference for SN2 because it's not involved in forming the carbocation. So now that I'm thinking about SN1, I'm going to erase the nucleophile. Now what matters is the carbocation. Well, once we form the carbocation, it's going to be solvated by the solvent. And which of these two carbocations is going to be more stabilized by the solvent, on the left or on the right? Are you going to be more stabilized by the solvent if there's a tight shell or a loose shell? Looks like maybe you're not sure about that. So, well, how are we forming the shell? We're forming the shell by forming bonds between the solvent and the carbocation. The only way you can form those bonds is if there's something on the solvent that the carbocation likes. The only reason we're able to form the solvation shell is because there's something here that it likes. In fact, just to be more specific again, suppose we were using here ethanol. Which part of the ethanol is going to actually be getting close to and bonding to the carbocation? Which atom? The hydrogen or the oxygen?
The polar oxygen.
Yeah, this oxygen with this delta negative. So what's going to happen is all the ethanols are going to orient themselves in ethanol, all the oxygens have big fat delta negatives because of their covalent bonds to the hydrogen. And therefore, they're all going to be forming strong bonds to this positive charge over here. Well, the more delta negatives we can get close to this carbocation, the happier it's going to be. So these hydrogen bonds are a stabilizing factor. These hydrogen bonds are a stabilizing factor because what does it mean to form a hydrogen bond to the carbocation? It means putting your delta negative close to the positive charge. Again, everything in chemistry comes down to the charges. Everything that seems complicated is really about the charges. Okay, so this is a case where we have somebody with a lot of big fat delta negatives, and that's why we're able to form this closed solvation shell. This guy doesn't have as many delta negatives, so it's not able to form those nice close bonds anymore. So again, which of these carbocations would be more stabilized, on the left or on the right? On the right. So would this be good for SN1 or bad?
Be good for SN1.
So protic solvents are best for SN1. Protic solvents are best for SN1 because we want to solvate the carbocation as tightly as possible. We want to solvate the carbocation as tightly as possible because that stabilizes it. And the big obstacle to SN1 is stabilizing the carbocation. On the other hand, for SN2, we do not want to solvate the nucleophile tightly because that would provide steric hindrance. And the big obstacle to SN2 is steric hindrance that blocks the nucleophile. Question?
So does inductive effect have anything to do with SN1?
Inductive effect. Let's see. What do you mean by the inductive effect here?
So if we have the carbocation and then let's say it's a tertiary carbon.
Right.
So will the substituted alkyl groups,
Right.
do they contribute anything to stabilize the carbon?
Oh, yeah, absolutely. That's right. In fact, that's much more important than solvents. So right now, we just happen to be talking about the effect of solvents on SN1 or SN2. But the effect of those alkyl groups is much more important. In fact, remember again, that's why if you look at the table in the handout, the table never mentions solvents, but it's all about whether you're primary, secondary, or tertiary, right? How do you figure out what row you're in on the table on page 3? Well, you check to see whether the alpha carbon is primary, secondary, or tertiary. Well, those are the same exact effects we were just talking about. A primary carbon is only connected to one carbon chain, whereas a tertiary is connected to 3. So those are definitely the most important factor for SN1 and SN2, whereas the solvents are not nearly as decisive. You can definitely be tested on them, but they're not as decisive for whether it's SN1 or SN2. Again, on test questions, the solvent isn't really going to affect what mechanism it is. It's more likely just to affect how fast the mechanism is going to go. Okay, so we can summarize this here. Protic solvents are best for SN1 because they tightly solvate the carbocation, and that stabilizes the carbocation, which is our big obstacle for SN1. Aprotic solvents are best for SN2 because they don't tightly solvate the nucleophile, so they don't provide steric hindrance, which is the big obstacle to SN2. Something I should mention is, actually, in your textbook, these would be called polar protic solvents, and these would be called polar aprotic. But we don't really need to discuss that because they're both polar, so that's not going to play any role. In this course, you're only going to use polar solvents, so we don't need to discuss what the significance of that is. They'll always say either polar protic or polar aprotic, but the important word isn't polar, the important word is protic versus aprotic. And the important thing is to be able to look at a solvent and see whether it has OH or NH bonds. That tells you which of these two categories we were going to be in here.